Hi, welcome back to Ed Talks. On today's episode, we're going to be covering a little bit different of a theory, string theory. Now, it's relatively a new theory. It's been around since the mid-1900s. So, it's involved in quantum mechanics, quantum physics. It started off in nuclear physics, but it didn't work out quite so well there. String theory is the theory of pretty much everything. It's how we can measure different things in the universe and our own planet, including different dimensional things. A little harder to observe that, but we can cover that later. So, the basics behind it is that all particles go one way, and they can be pulled out into strings. So if you think of a particle like a string, then you start going the right way. There's different kinds of particles. You have fermion particles and boson particles, made by two different people, and they have two different properties. We won't get into the depths of those properties today. We can cover that for a later time. But more about string theory itself and less about the particles involved in it. Now, there's different kinds of string theory itself. There's M theory, string theory, superstring theory, supersymmetry. Now, all that is different types of string theory that is encompassed into the theory of everything. Now, if you have just base string theory and you have your different particles, you can measure them in a variety of ways. Some are a little harder to measure than others, but can all be measured. Now, M theory is the one that encompasses the most. And M theory is based off the idea of 11 dimensions. We live in a three-dimensional universe, height, width, and length. If you include space and time, that gives you 4 dimensions. So you have to come up with 7 more dimensions to do the M theory. So you just got to kind of, think through there. A little hard to measure. The consistency is hard because we don't actually have the ability to physically observe those different universes. But with a little bit of creative thinking, it can be done. Now, it's used to measure things such as black holes, solar mass, and a variety of other things to do with celestial bodies. So, with the celestial bodies, when you measure the mass, the density, and all that, that is what string theory is for. Originally, Einstein had it as the theory of gravity, something along those lines. Relativity, theory of relativity, there it is. All right, so the theory of relativity was slowly developed over time into string theory. Like I said before, it's a more modern theory, so it hasn't been around very long to be tested extensively. So, along with M theory, you have 2 other kinds of theory. One involved the use of 12 different universes and the one of 24. If you thought it was hard to imagine 7 different universes, shrouding all those in becomes a real headache later on, I can tell you that. So, we have all these different universes and the ability to measure all the different ones and different variances. The only issue, well, I should say the largest issue, rather, with string theory is because you have all these universes you're just thinking about that aren't really there, you end up with inconsistencies in your data. Inconsistencies can lead to things not being right, hence the word inconsistencies. However, it is the closest way we have to measure certain types of events, such as black holes, like I stated earlier. It's very hard to measure a black hole because you can't actually see it. You just have to look at the way it affects light around it and objects around it. And that's what string theory helps to do. It helps to measure the way the particles, the strings, all the physics and stuff interact with things that are harder to observe with the naked eye or even with a telescope, because you can't see a black hole with the naked eye. Come on now. So, the only way we have to measure it all. Therefore, you have to use some imagination with the extra universes, because again, we live in a 3-dimensional world. Length, width, height. If you add space and time, that gives you 4, but those aren't included in standard measurements. Now, when including space and time, they're counted as 1 dimension, even though they're 2 words. Because time and space can't exist without one another. You can't have time without space. You can't have space without time. It can't be done. I don't know why. I didn't make the rule. Someone else did. So, now that you know the fundamentals behind it, we can get more in depth with the different particles involved in it, like I stated earlier. You have bosons and fermions, I believe is how it's pronounced. A boson particle always has a sister particle, and it ends in an ion. So if you have one particle in aon, the other one would be an eon. Both end in an ion. Same thing with the fermion particles, except for one will start with an S. So if you have an electron, you have a sestron, because it starts with an S. See? That's all there is to it. With the fundamental knowledge, you can conduct your own experiments and gather your own data and your own research at home. Now, I'm not going to go in depth of how to do that, but you can figure it out. So, testing at home. It's a little hard to do because you need some special equipment you might not have, maybe a telescope or two, maybe a way to measure the speed of light. But if you get those things, it can be done. The internet is also a great tool. Use it. Now, we've covered everything in string theory, for the basics at least. Think of it as string theory for beginners. So, more advanced stuff can be learned elsewhere. I'll try to cover a little bit more here, but we won't get too in-depth with it. I don't want to overwhelm you with too much information at one time. So, as a recap, different dimensions. We live in a three-dimensional world. You can think of it in 4 dimensions if you include time and space. You need 11 for an M theory, string theory. You need 12 for another kind, and 24 for the final kind. Again, a lot of universes, a lot of different dimensions. But it's all inconsistent when you measure it because they don't physically exist. You just have to have the mathematics behind it. Now, the particles. Remember, all of them have a brother and sister particle. One particle has to have an equal particle. Remember? All right, good. So, with the equal particles balancing each other out, it's simple to understand the mass and the size of celestial bodies. So it's easy to understand the size and mass of celestial bodies. So, like I said before, as previously stated, black holes. You can't watch them, can't see them, they're black. Go in a dark room, turn off the lights, you can't see nothing. But you know it's dark because there's no light. How do you see if the room's dark? You turn on a light. Same way with a black hole. You just shine a light by it. If the light bends, you know there's a black hole there. It's that simple. A little hard for us to do from Earth, but we can see light in space. It's there, it's everywhere. Every star's a light. It's that simple. Just think of it as stars, big flashlights. Easiest way to measure stuff in space is look at a star. Back to string theory though, because we kind of sidetracked there to give you some more information. So let's get back to what this video is all about. String theory, the theory of everything. You use it everyday life. It's used to calculate anything and everything, hence the term theory of everything. Now, me and you might not use it, but people in NASA do. People in the observatories on top of mountains do. Scientists do. It's everywhere. So, with that being said, I hope that you now have a basic understanding of string theory. And with that, I hope you have a fantastic day and tune in next time for another episode of Ed Talks.
Hey guys, thanks for watching. If you enjoyed this show and want to see more like it, like, share, subscribe, and check us out on social media. See you all in the next one.